Now let's understand about the concept of work transfer. When we hear the word work, the very basic definition comes into our mind, that force into displacement. But that is basically the definition of a mechanical work, in which an object is displaced from one position to another with a working force, and the work is given by W is equal to F into D, where D is the displacement, and this is what a mechanical work is. But when we are dealing with the thermodynamic work, the definition is quite analogous but different. In case of thermodynamics, instead of an object, we are having a system, a thermodynamic system. So how to understand if work transfer is taking place in a thermodynamic system? See, I told you earlier that a system boundary differentiates a system from the surrounding, and surrounding is the whole universe itself. So if there is any change in this system boundary, then we can say that some work transfer has been occurred in this particular system. It can be contraction or expansion, doesn't matter, but if the boundary, the system boundary is changing, then we can conclude that work transfer has taken place. Now let's take an example of a nozzle. Here let's assume a fluid is flowing from one end to another, let's say from point 1 to point 4, and I have bifurcated the nozzle into 4 parts, into basically 3 parts having different boundaries, that is denoted by this imaginary line. So if a fluid is moving from point 1 to 2, then 2 to 3, then 3 to 4, what is happening? The boundary of the system, if we are considering this particular periphery of the nozzle of the system, the boundary of the system, if it's getting changed, then we should have some work done. But that's not the case. Work is crossing boundary, or we can say the boundary keeps on changing, although the work done, the work transfer is 0, because we are not getting anything out of it, because work is what is a form of energy. So this particular scenario would be regarded as a free expansion. So we can conclude that if the contraction or expansion of system generates work, we can say that the work transfer took place. And more accurately, if work is changing boundary, that it can be said that work transfer is happening. However, this too is also not true always, just like in case of nozzle. Now let's understand about PDV work, or to be more precise, PDV work for a closed system, because for open system is completely different. That we are going to understand in the coming lectures. Let's assume a piston cylinder arrangement, the same one without any exhaust valve. Let's say we are applying a force F to the piston, and the system is being displaced by a small displacement, let's say dl. So what will happen? The gas that is or the air particles or anything that is contained inside the cylinder, it will try to resist this movement. So there would be a definitely would be a reaction force against of F. So let's take it as R. So as far as equilibrium is concerned, when there will be a point when we have to apply some additional force to overcome the reaction, at that point equilibrium will be reached. That means the reaction force would be equivalent to the force applied, R is equal to F. So for the equilibrium, summation of F is equal to 0, that will give us R minus F is equal to 0. Now at this particular instance, let P be the pressure of the molecules present inside the cylinder. So as we know, pressure is what? normal force per unit area, and here normal force is what? R. So R by A would be your pressure, or R would be equal to P into A. Now let's find out the mechanical work here. Work done is what? Force into displacement. So if we are considering for this small element of this small elemental instance, basically where the piston is being displaced by a small displacement of dl, we have dw is equal to F into dl, and F is what? The reaction force itself. That means Pa into dl, and A into dl would be what? Your volume. So this gives us dw is equal to pdv. This is the work transfer, and if we want to know the total work transfer of the system, then we have to integrate it, because we are trying to comprehend it with an elemental instance. So integration of dw is equal to integration of pdv. Now let's make a PV diagram, which is the very important concept in thermodynamics. When we make a PV diagram from point 1 to 2, here the change in volume is V1 to V2 and change in pressure is P1 to P2, because we are taking initial and final. We are not taking a elemental instance. But if we take a elemental strip in this PV diagram of, let's say, dV, as per as the x-axis, as per as the volume axis is concerned, then the integration of pdv would be the work done that would be equivalent to the area of PV diagram for the process, or we can say the area under PV diagram gives the work done. Thank you so much. See you in the next lecture.